Hello, my name is Danny Nolan and I'm the Director of Chassis Sim Technologies. Welcome again to this latest episode of Dan's Vehicle Dynamics Corner. What we're going to be discussing in this episode of Dan's Vehicle Dynamics Corner is the importance of motion ratios. Now, when we think about motion ratios, in some respects, sometimes I think of them as the almost forgotten bit of when you're doing race car setup and when you're putting together a vehicle model. Yet, even though they're sort of forgotten and not thought about as particularly sexy, I can tell you right now, getting your motion ratios right is such a critical element of getting your race car setup correct, because the motion ratios is if you get these right, you'll be amazed at how everything falls into place. I'm going to show, and I'll show you a practical example of that at the end of the tutorial. So really, this is more really sort of, even though what I'm about to discuss is incredibly obvious, it's nonetheless a very, very important thing for you to remember and for you to keep in mind. So let's get started. Right. When it comes to deducing motion ratios, what we want to classify is the ratio of how the damper moves over the ratio of how the wheel moves. Now, from time to time, you will see race car manufacturers state that the other way around. But here's the kicker. The reason it is so important is because the spring rate the tire sees is given by wheel rate is equal to motion ratio squared times spring rate. This, ladies and gentlemen, is why classifying your motion ratios is such an important job. And it's actually one of the most overlooked jobs that you'll see. But if you get it right, you will just be amazed how things fall into place. And really, what we want to do is we want to plot wheel movement over damper movement from full droop through to full bump. Now, I say from full droop through to full bump because we need to get a really good idea of what it's actually doing. Now, in terms of the practicalities of doing it, it's actually not as difficult as you think. This is what you need to do. If you're running, say, something like an open wheeler, if you're dealing with something like an open wheeler, what you need to do is simply take the spring. All you need to do is take the spring off, and what you do, get the car in the air and let it go down to full droop. Get a car jack, and what you get a car jack, and what you do is that typically, if it's something like, say, an open wheeler, you'll grab a table with a level next to the tire so you can get a good level. If you're dealing with something like a touring car, you do exactly the same thing, except what you would do is basically put something like a bit of a little bit like, say, a little bit of pipe on the wheel nut so you can go through. But the whole idea is you just want a fixed level so you can measure how the wheel goes up and down. And typically what you'll be doing is that you'll grab a set of verniers and you'll be simply plotting wheel movement over wheel movement on damper displacement. You also do the same thing with the bar movement. And what you would do with the bars is obviously you disconnect disconnect the bar, but you would leave the motion ratio linkage as same. And all you're doing is that you're plotting how the motion is that you're basically plotting how that motion ratio drop length is moving. So consequently, it doesn't have to be ultra advanced. And indeed, I know that there are a lot of kinematic programs out there that will calculate motion ratios for them. I mean, WinGeo and Susprog are cases in point, and they do it very, very well. That being said, I always do advocate measuring this because 99 times out of 100, programs like WinGeo and Susprog will get you right there. However, there's that 1 out of 100 case that can ruin your whole day. So, which is why I always advocate measuring it. Now, in terms of some motion ratio approximations you might find useful, if you're dealing with a touring car or something that's not mounted to a bell crank, this is an old trusted little formula that you can use. So effectively, you measure the pickup point from where the damper connects to the lower arm to where it pivots, divided by the length of the lower arm, and the C on D is effectively measuring the length from the end of the lower pickup point to the instant center, and D measures the length of the top of the contact patch to the instant center. Now, if you're in a rush and you don't have your kinematic programs to hand, look, you can approximate it with A on B, but that's if you're in a rush. If you need sort of a rough rule of thumb to go, okay, I just need a rough rule of thumb of what my motion ratios are, you can use A on B, but if you really want to nail it down, it's basically A on B multiplied by C on D. The other motion ratio approximation that you can use is if you've got a push rod operated open wheeler open wheeler arrangement. Now, in this situation, what you've got to do is that you measure the angle that the push rod's at, and you've got and you measure the rocker and you measure the rocker motion, the rocker arms, and what you'll find here is the motion ratio is A on B multiplied by sine theta. Now, please bear in mind, this is an approximation. This is there to help you really sort of nail down what the motion ratios are, so you get some sort of rough expectation of where you should be. Your next step after you do this is that you go through and measure up the motion ratios properly. And what we've got in this little Excel spreadsheet is that you'll see this is a motion ratio stuff for some Star Mazda work that I did a couple of years ago. And what we've got is what I did was that as we discussed before, I took off the springs and bump rubbers. I just left the springs connected, got the car in the air, and all I did was I just simply grabbed a table, moved it near moved it near to where the center of the contact patch is. Just grabbed a couple of clamps, basically clamped a fixed level to the table. And what I did was I simply moved the wheel up and down. And as you can see, I plotted my wheel deflection and I plotted my damper deflection, and that is what I got left. Now, the beauty about this is, and this is a little technique that's gold, because what it does is that you can do this on the fly. So if you make a mistake, it's going to show up really, really quickly. Now, as you can see here, the motion ratios here are actually very, very linear. And usually, if you've got a really nice continuous graph, that's showing you that you're really, really on the money. So this is why I always advocate doing the. This is why I always advocate, but plotting it as you go. Because if you screw up, you're going to see a discontinuity. So that's a really, really handy tip. Now, in terms of what to look for in the data, when you get your motion ratios right, you're going to get something like this. Now, what we've got here is a preliminary simulation of a touring car that we did these measurements on. What the actual data is coloured, the simulated data is black. So this is a first cut, but you know you're on the money when you're starting to get instant roll and pitch correlation off the bat. In terms of what to be looking for, I can tell you right now, if we just take a look at this pitch comparison, which is these the second and third last bottom graphs, they're basically spot on straight away. If you're getting those spot on straight away, that's a really good indicator that that's a really, really good indicator that your rolls are that your mainspring ratios are absolutely spot on. Also, too, just zooming back out, looking at where we had equivalent speeds, we could also see that our roll motion ratios were also close. Now, initially, when you're doing this, particularly when you run up the first model for the first time, you are not looking to a roll and pitch correlation within the nearest nanometer. But you're looking for, but you are looking to say within, depending on your spring rates, how big the car is, rough rules of thumb, plus or minus a couple of mil on your initial cut. If you've got that, you're laughing. What you need to be really mindful of is a really telltale sign that you've got your motion ratios wrong is when you've got massive discrepancies in how the simulated pictures look and the actual pictures look. The other thing that you need to be, and the other thing too, when you've got your roll motion ratios wrong, is when you've got really, really big discrepancies in the roll. I mean, like in a factor of two. That is when you know that you've got something wrong. But really, I cannot stress enough the importance of working through an exercise like this because it's going to tell you so much about what your car is going to do, and it's really going to nail that. And not only does this has implications for simulation stuff, but it also has some implications for things like doing lateral load transfer distributions and really quantifying what you want to do. So really, I cannot stress enough the input and really the reason this is so important is because your wheel rate, which is what your tires are saying, is effectively motion ratio squared times spring rate. So I will leave you with that thought and really get out there and deduce your motion ratios.